Hi. Now let's continue to discuss about diffusion in a more microscopic scale. And I will introduce the concept of random walks. So let's consider about the story of diffusion at the molecular scale. You probably have heard about Robert Brownian motion before. So let's assume in 1828, Brown published about this observation. So you look at these tiny dark points as a water, and this yellow one as a pollen. So he observed the trajectory of this is kind of a random, and it moves on top of the surface of a water, and that's what he observed. So that's kind of interesting. And what if this pollen has a much smaller one compared to this invisible molecules surrounding this fluid? So the next one, we can see this. You see this moves much faster, and so it compared to, it depends on the size of the pollen, why he was interested in why this one moves at this kind of random trajectory, and that we call as a Brownian motion. So Brownian motion is presumably random movement of particles suspended in a fluid, resulting from fast collisions by molecules in the fluid. At the time, we did not know the presence of these molecules. So, so even that detail was not worked out. And collisions between molecules inside the liquid turn out to be a lot, very fast. That means like in 1 second, trillion times of this interaction of collisions happening. So that results in the net of the gross movement as a random motions of this particle. So you can see, and later in 1905, Albert Einstein, in fact, contributed a lot of this by proposing that this is the evidence of presence of atoms and molecules in a macroscopic scale, resulting Brownian motion. So we consider these two phenomena, that what factors can affect the speed of diffusion. So you can think of first the size of the this particle or molecule matters, and also of course the shape of the molecule would affect, and the surrounding fluid like this liquid, the viscosity would affect the speed of this diffusion phenomenon. And of course, these microscopic energy of the movement is dependent on the temperature. Temperature is a measure of this thermal energy. So this phenomenon now is mathematically, we call it as a random walk, that the net molecular motion arising from random course collision. So this is just for reference material, so you don't have to like memorize, but I just want to cover this to give you some sense of this. So the question was instantaneous velocity of a small particle, such as a protein lysozyme, which has a molecular weight of 14 kilogram per mole, or 14 kilodalton. And to consider this issue at the microscopic scale, we need to understand a little bit of kinetic energy associated with this movement. So that is related to this thermal energy represented by a Boltzmann constant. So it's along one axis, this kinetic energy is a 1/2 kT, and this K is Boltzmann's constant, and the T maybe room temperature around 300 Kelvin. So we can see this energy caused the kinetic energy of this mass m and velocity v on average, then 1/2 mass times average velocity square would be like 3 axis of this movement of thermal energy, 3/2 times kT. Then we can solve this equation to find out the average velocity of this particle. And that is turned out to be about 23 meters per second. And this is a quite fast movement. So, yeah, the answer is 23 meters per second, and it's super fast, faster than what we can actually move. And due to the random collisions in the lysosome media, the protein is forced to wander around to execute a random walk in all directions and spread out, leading to a simple diffusion. So now I want to introduce how to describe this as a, to analyze this phenomenon as a, like the simplest possible, the one-dimensional random walk concept. So to characterize this diffusive spreading, let's simplify this problem to consider the motion of particles along one axis only. And the particles start at time t at position x equals 0. And let's execute a random walk. Yeah, random walk you can consider as a drunken person, fully drunken person start to move around. Now it's a one dimension, means that person can move, go this way, the other way, step, he has a step. So each particle steps either to right or left. Once every, let's say, time constant is tau second or time step. And the velocity as a v sub x. So it can be positive plus vx or minus vx. And of course, the distance will be at each step is the velocity times the time step, which is a vx times tau, or plus or minus. And now this is the nature is random. So the probability of going to the right at each step and left, what would be the probability? Because this is random, it's equally probable to go to the right or left. So the probability should be 0.5. And successive steps are statistically independent. So what it means is, you know, after one step, the previous step doesn't matter for this step to decide whether to the right or left. So we can call this as a like fully drunken person, no memory, meaning that no accumulated previous history will affect what's happening at this point at time t. So, and also we can assume some reasonable assumption that this particle movement will be independent from other particles. So each particle moves independently of all other particles. In fact, this is only true in a reasonably dilute conditions. And so we are interested in measure of how much of spread of this drunken person at the end of the day. So overnight he was wandering around, and we want to see how much he actually moved around. So the measure of distance traveled by this drunken person performing random walk, or this particle traveled diffusing, is because this can go to right or left. There's a sign involved, so a reasonable way is to remove the sign. And an easy analytic way is just square of this displacement and then make the unit as a distance by putting square root. So that's like square of the displacement of the average, and then we put the square. So that means root mean square displacement, or RMS value. So for this, we will solve with a board exercise.